Welcome to the deep dive, where we don't just skim the surface, we really plunge into the fascinating currents of knowledge, bringing you insights from the sources you share. Today, we're embarking on a journey that might just fundamentally alter how you perceive the very tools we use to build our digital worlds. Think about it. What if a programming language isn't merely a meticulously crafted tool? A static collection of syntax rules and logical commands. What if instead it could be something far more profound? A living, breathing, evolving ecosystem. We often approach code expecting pure, predictable logic, right? A clear instruction set that machines just execute perfectly. But some systems, even those born from really rigorous engineering, they achieve this kind of vibrant life that goes way beyond their initial design. They become something much greater, more influential than just the sum of their parts. And when we think about languages that have achieved this kind of unexpected emergent life, Python really stands out. It's arguably the most extraordinary example. Its incredible journey isn't just a story of brilliant technical design, though there's certainly plenty of that. No, it's really a profound narrative of emergence, of a system evolving in these dynamic, self-organizing ways that, well, its original creators probably couldn't have fully mapped out or anticipated. It's really a testament to how raw informational constructs, pure code, when you put them in the right environment, can spark genuinely new forms of organization and impact.
Precisely. And our mission today is to truly understand this remarkable transformation, to look beyond just a simple chronology and instead grasp the underlying systemic forces at play. To do that, we're going to employ a powerful analytical lens. It's known as the River of Reality framework. This framework, it's rooted in the foundational principles of general systems theory, and it lets us dissect Python's 3-decade journey, tracking its continuous emergent process. We'll trace its path from what began as a simple informational construct, pure idea, pure code, all the way to the global force it is now, shaping industries, science, even our digital culture. So to appreciate the framework, let's briefly define its core components, the fundamental elements that make up this river of reality. Imagine reality itself as this grand, dynamic river, always flowing, always increasing in complexity and structure. At its source, we find 3 fundamental elements. Their interaction drives all change and creation. First, there's energy, and this isn't just power like electricity. It's the potential for change, the dynamic tension, maybe an unmet need or some disequilibrium that propels systems forward. It's the impetus. Second, we have material. This is the tangible stuff, the substance of existence, the raw ingredients, resources, the components that change acts upon. And third, crucially, there's information. This represents the organizing patterns, the blueprints, the rules, algorithms, the knowledge that brings structure and coherence to the other two. Now, as these 3 elements, energy, material, and information, flow and interact, they don't just mix together randomly. Instead, they converge, they interweave, and they give rise to what systems theorists call nested hierarchies of systems. The really profound insight here is that each new level in this hierarchy isn't just a bigger collection of the lower parts. It exhibits novel, emergent properties, things that were entirely absent, completely unpredictable in the individual components below. It's not just adding things up, it's a profound process of transformation, creating something genuinely new.
That's a powerful way to frame it. Okay, let's really unpack this using Python's story then. So with this River of Reality framework as our guide, we're going to navigate Python's story across 3 distinct levels of emergence. We'll witness its evolution firsthand. First, we'll delve into its genesis, its very birth as a simple informational construct, basically, the pure idea and initial code. That's what we'll call level 1 emergence. Then we'll move to level 2. That's where we see its evolution into a self-regulating, living community, adapting, growing, metabolizing feedback, like an organism in its environment. And finally, we'll track its ultimate arrival as a culture-shaping global force, demonstrating not just survival, but real purpose, self-awareness, collective choice on a grand scale. That's level 3. What you, the listener, can expect from this deep dive is really much more than just a history lesson. You'll witness firsthand how this humble serpent, born from a programmer's quiet insight, grew incrementally, absorbing energy and material, organizing information, to become a mighty river in its own right, shaping the technological landscape we see today. This isn't just about understanding Python's past. It's a powerful masterclass in systems thinking. It offers profound lessons applicable to any complex adaptive system you might encounter, in your own fields, daily life organizations, markets, ecosystems. So let's dive into the current. Okay, so every grand river, every complex system, it has to start somewhere, right? A source, a very specific set of conditions that gives rise to that first trickle. For Python, that source wasn't some massive corporate initiative or a huge university project. Instead, it emerged from the quiet halls of a research institute in Amsterdam, late 1980s. And, crucially, from the creative discontent of one brilliant programmer, Guido van Rossum. You have to picture the scene. Nascent days of personal computing, the internet was still mostly a research network, not everywhere like today. Developers were grappling with pretty significant limitations in their tools.
Right. And what's really fascinating, Python's origin story doesn't begin with some big success. It starts with what you might call a noble failure. Before Python, at the Centrum Wiskundi and Informatica CWI, where Guido worked, there was a language called ABC. ABC was pretty revolutionary for its time, designed with this almost singular focus on simplicity, teachability. It aimed to make programming accessible, elegant, straightforward, especially for non-programmers. It even pioneered using indentation for code blocks, that feature that became, a hallmark of Python itself. But despite its innovative design, its noble intentions, ABC ultimately remained kind of closed off from its environment. Its technical strengths were really constrained by the practical limitations of the era. Distribution, which is absolutely critical for a language to gain traction, build a user base. Well, distribution was severely crippled. This was pre-internet explosion, late 80s. ABC mainly relied on cumbersome floppy disks, which meant it just couldn't spread efficiently, couldn't reach a wide audience, couldn't get that critical mass of users and feedback needed for wider adoption. Its elegant information pattern was basically trapped by its material limitations.
So ABC, despite its goals, didn't spread widely. But how did that failure, paradoxically, lay critical groundwork for Python? What specific lessons did Guido take from it? Because its demise wasn't really a dead end, was it?
Not at all. Its demise actually left behind fertile ground, kind of a conceptual and practical void that highlighted exactly what was missing. Guido, having worked on ABC, saw its strengths, clarity, expressiveness, but he also intimately understood its fatal flaws, its lack of extensibility, its inability to easily interact with the operating system, its sort of insular nature. So this failure wasn't just a mischance, it was a crucial illuminating precondition for Python. It underscored that a language needed not just elegance, but also extreme openness and practical utility to really thrive. This experience, in many ways, it provided a clear, almost negative space blueprint for what Python needed to become. It really highlights how often, in innovation, perceived setbacks can actually clear the path and provide invaluable, hard-won lessons for future breakthroughs.
Okay, so with that fertile ground laid by ABC's journey, this is where those primordial components of our river of reality, framework, energy, material, information really start to converge, sparking a completely new beginning for what would become Python. It's like watching separate currents suddenly come together to form a powerful stream. So the energy for Python's creation, that raw potential for change, was born directly from Guido's own frustration. He was working on a really complex project, the Amoeba Distributed Operating System at CWI. For this cutting-edge work, he found himself constantly stuck in this kind of technical limbo. On one hand, you had the high-level simplicity of shell scripts, great for quick tasks, but fundamentally limited for complex system programming. On the other, the low-level complexity of C. Immense power, sure, control over hardware, but incredibly cumbersome and slow for rapid prototyping, writing utilities, or just stitching components together quickly.
Exactly. This friction, this palpable gap between what was and what could be, wasn't just a minor annoyance for Guido. In our framework's context, this represents a significant reservoir of potential energy awaiting release. It was a critical, unmet need in the computing landscape, a problem just screaming for an elegant solution. Existing scripting languages back then, like Perl or TCL, were often seen as clumsy and inadequate for the kind of robust yet flexible scripting needed in distributed systems. They each had their own quirks, limitations, making them less than ideal for bridging that crucial gap between high-level abstraction and low-level system interaction. This constant struggle, this efficiency bottleneck, really generated the dynamic tension that Python would eventually resolve.
And what's particularly insightful, what adds a uniquely human element, is that this catalyst, this precise moment the potential energy found its release, happened during a quiet Christmas holiday. It wasn't some corporate mandate or a big team project. It was a period of focused, uninterrupted creativity for one person. This personal, almost intimate setting let Guido channel his expertise, his deep understanding of language design, and, crucially, his frustration into something new. It underscores how huge breakthroughs can start from intensely personal moments of insight. But Guido wasn't just working with frustration in a vacuum, right? He had this rich substrate of existing ideas and technologies. That formed the material of Python's existence. He wasn't starting from scratch. He had a wealth of prior art to draw on, like a sculptor with different clays and tools.
Exactly right. We can point to several specific examples that served as Python's genetic material and robust substrate. First, and maybe most directly, was the structured elegance of ABC. Its innovative use of indentation for grouping statements wasn't just aesthetic, it was a critical technical decision. It fundamentally contributed to readability, reduced syntactic clutter, made code visually cleaner, easier to parse for humans and machines. This feature, almost like informational compression, became core Python DNA, differentiating it from languages using braces or end keywords. Second, the power and portability of the C language was absolutely essential. Python itself was implemented in C. This wasn't just convenience, it was strategic. It provided a robust substrate for implementation. C allowed Python to be performant, have fine-grained control, and crucially be highly portable, meaning it could run on almost any OS with a C compiler. This gave Python its bedrock stability and ability to interface with low-level calls, precisely what Guido needed for Amoeba. Without C, Python's reach would have been much more limited. And third, concepts from other cutting-edge languages then, like Modula 3, they contributed significantly to Python's architecture. Modula 3 influenced things like modules for code organization, exceptions for structured error handling, even some object-oriented features. Guido wasn't just cherry-picking, he was thoughtfully integrating proven, elegant solutions from the wider programming ecosystem, combining them in novel ways. These weren't arbitrary, they were carefully selected and integrated into a synergistic whole.
So these weren't just random bits and pieces. They were carefully selected raw materials, the elemental building blocks waiting for a pattern to organize them. It really reinforces the idea that innovation often isn't about conjuring something totally new out of thin air. It's more about intelligently combining, remixing, refining existing ideas and tech in novel ways to solve a pressing problem, a masterful act of synthesis.
Which brings us neatly to information. In Python's genesis, this was Guido's singular act of synthesis. He took that latent energy from his frustration and those raw materials drawn from existing languages and organized them into a coherent, self-contained system. This was the moment the distinct pattern emerged, providing the rules, the structure, the very identity of Python. The blueprint finally brought to life.
And the tangible manifestation of this new informational pattern, the first Python interpreter. Think about what it embodied. Clean syntax, powerful data types, and clear semantics. Not just buzzwords, concrete design choices. Python offered dynamic typing variables didn't need explicit type declarations, speeding up development. Its powerful data types, like flexible ifs and dictionaries right from the start, made common tasks much simpler than in C. And its clear semantics meant Python code generally did what you expected, reducing ambiguity, cognitive load. These were the simple, elegant rules governing this nascent system, designed for clarity and productivity from day one.
And we even have a specific milestone for this Level 1 emergence. The release of Python, 0.9.0, in February 1991. If we connect this to the bigger picture, using Kenneth Boulding's analogy, this initial release was like a beautifully crafted clockwork. Complete, functional, exceptionally well-designed. It worked perfectly by its internal logic. But at this stage, it was still very much an artifact, a closed system, really. Order created, yes, brilliant engineering, but essentially a beautiful machine waiting to truly connect with its environment, to be set free, interact with the broader world beyond Guido's immediate control. Immense potential, but not yet life in the grand river of reality.
So Python at this stage, a masterpiece of design, brilliant engineering, but still in a controlled environment, a blueprint, not a bustling city, a complete self-contained informational pattern. So the crucial question we're left with now for you, the listener, is this. How did this carefully crafted clockwork break free? How did it begin to truly live in the vast, unpredictable river of the real world? How did it transition from a perfectly ordered artifact to a dynamic, adapting, and ultimately living organism?
Well, a system, no matter how brilliantly designed, remains just an artifact, a static thing, until it becomes an open system. This transition is fundamental. It means the system becomes capable of continuously exchanging energy, material, and information with its environment. And this critical distinction brings us to what I consider the single most important decision in Python's entire history: Guido's choice, supported by CWI, to release it as open source.
Here's where it gets really interesting, where the framework meets a pivotal human decision. How did this open source release even happen back then, before the web was everywhere? In those early internet days, this meant posting the code to the Usenet group alt.sources. This wasn't just casual sharing, it was a deliberate act that, metaphorically, opened the floodgates. It released Python into the wild, into an environment where it could truly interact, get feedback, start its journey as a complex adaptive system, like releasing a boat into the ocean for the first time.
Exactly. This is precisely when the clockwork was submerged in the river. And in doing so, it began to live.
This moment undeniably marked Python's transition to a Level 2 system. It moved beyond a mere static construct and started showing characteristics we associate with biology: a vigorous metabolism, rapid adaptation, sustained self-driven growth, all critically powered by one fundamental mechanism: feedback. The system began to learn.
It's quite a leap thinking of a programming language in such organic terms, but Python really did start exhibiting these characteristics. It wasn't just static instructions anymore. It was reacting, changing, evolving in real time. And the powerful engine driving it all, the fuel sparking its life, was indeed that critical mechanism of feedback.
What's truly fascinating is how quickly Python developed a robust metabolic engine. The early USAC community, those initial adventurous users combined with Guido's personal email inbox, rapidly became the system's central hub for processing information, almost like an organism's digestive and nervous system, constantly taking in nutrients and stimuli.
And the feedback loops that emerged were immediate and powerful, forming this dynamic, self-reinforcing cycle. Think about it. Once the code was out there, it wasn't just passively consumed. Enthusiastic users, ranging from NASA engineers using it for complex simulations, maybe mission planning or data analysis, to hobbyists automating mundane tasks on their early home computers, they began sending a constant stream of information back to Guido and the community. These weren't passive users. They were active participants, beta testers, co-creators. Bug reports were a crucial form of negative feedback. Not just complaints, vital data points highlighting errors, weaknesses, guiding corrections that improve stability, robustness, reliability. Without this, problems would fester. But equally important, feature requests and contributed code were a powerful form of positive feedback. Users suggested new capabilities, even submitted entire modules, fueling incredible growth, expanding the language far beyond its initial design. A dynamic cycle: input, processing, output.
Right. This interactive process of consumption, processing, and excretion of information, the flow of user input, bug reports, ideas, code contributions, is precisely what allowed Python to rapidly evolve beyond its initial blueprint. Connecting this back, it's an elegant parallel to biological systems, which thrive on constant interaction, adapting and growing based on sensory input and resource exchange. Python 2 was learning, correcting, growing through this relentless stream of communal input, demonstrating a profound capacity for system-level learning and self-improvement that was truly emergent.
And from this dynamic of feedback and community interaction, a core survival strategy emerged, a philosophy now synonymous with Python, batteries included. This wasn't some top-down directive. It was an organic, pragmatic response to the community's needs and contributions.
That's right. As the community contributed a wealth of useful modules, everything from handling email protocols like SentientTplib later, to basic web servers, http.server, or interacting with the OSOSession, a deliberate, crucial decision was made. Many of these commonly needed functions were integrated directly into the language's standard library. So when you downloaded Python, you didn't just get the interpreter. You got a huge suite of ready-to-use tools. This philosophy made the Python ecosystem significantly richer and far more self-sufficient right out of the box. It dramatically lowered the barrier to entry for newcomers because developers didn't have to hunt down and configure basic functionalities from different places. They had a comprehensive toolkit right there. This made the language immediately useful for a vast array of tasks, from simple scripting to more complex development, distinguishing it sharply from languages needing extensive external setup.
And that, you see, was a clear and powerful evolutionary advantage in the competitive landscape of programming languages back then. In an environment where languages like Perl or TCL often required users to piece together functionalities from various, sometimes incompatible external sources, Python's batteries included approach meant it wasn't just an engine, it was a fully equipped workshop. This practical utility immediately set it apart. It significantly accelerated adoption, especially among those valuing rapid prototyping and minimal setup, and cemented its place as a go-to tool, fostering a much broader user base.
As Python continued to widen its stream, the community itself grew exponentially, rapidly transforming from a loose collection of individuals into a big family. And with that growth, more diversity of opinion, usage, contribution came an increasingly pressing need for more complex, formalized organizational structures to manage this burgeoning ecosystem. You just can't run a global family of millions with the same informal rules as a small gathering.
Right. This inherent need for structure, for a higher level of organization, it manifested early on. We can look at the first Python workshop in 1994. Seems tiny now, just 20 attendees. But this humble gathering, not a top-down thing, was effectively the system's first act of self-organization. Think of it like cells gathering to form a coherent organism, a new level of complexity emerging from simpler parts working together. It was the community consciously deciding to meet, discuss, share, collectively steer their shared creation, recognizing the need for coordination beyond just individual emails. These early workshops were vital.
And this process of self-organization culminated in a truly pivotal moment for Python's long-term viability. The creation of the Python Software Foundation, the PSF, in 2001. This wasn't spontaneous, but a deliberate strategic move born from necessity. What's particularly fascinating is the context. This happened during significant economic upheaval, the precarity during the dot-com bust. The community collectively realized Python's survival, its future, could not be tied to the fate of a single corporation that might face instability or change direction. They saw the vulnerability of having Python's IP potentially under control of a commercial entity that could go bankrupt or restrict its use.
So, the PSF emerged as far more than just a legal entity. It was truly the system's dedicated cardiovascular and nervous system. It became an independent entity to hold the intellectual property, ensuring Python's open source license would stay free to manage finances for core development and community stuff, and crucially, to steer the language's development through committees and working groups. This provided the essential institutional framework for long-term health, stability, continuity, safeguarding it from commercial or individual interests.
Ultimately, the PSF was absolutely crucial. It ensured Python's long-term health by providing a stable, neutral steward. This effectively transformed it from a project into a self-sustaining institution. This was definitive proof Python had achieved level 2 emergence, not just a living organism reacting to its environment, but one capable of sophisticated self-governance, strategic planning, ensuring its own long-term viability. It had institutionalized its emergent life.
It's quite a leap, isn't it? From a quiet holiday project to a globally recognized, self-governing institution. But now we have to ask you, the listener, how does a self-sustaining organism then transcend its own existence? Move beyond mere survival and actively begin to shape the world around it, fundamentally changing the environment it operates in. That's our next big question as we move to level 3, where Python becomes a truly mighty river, shaping entire landscapes. By the early 2000s, Python had undeniably become more than just a language. It had evolved far beyond being simply a vibrant, self-regulating community. At this point, it was a force beginning to reshape its environment, actively carving out new paths, establishing new norms, profoundly influencing tech directions globally, becoming indispensable for entire fields.
This is where its journey truly enters level 3, transitioning into a cultural, philosophical, and societal phenomenon. We start seeing emergent properties characteristic of truly complex social systems. Not just adaptation and self-organization, but also a discernible collective purpose, a deep sense of self-awareness, and a robust capacity for collective choice. It's no longer just reacting. It's acting with intention, shaping its own future, and, crucially, shaping the future of countless other projects and people. The river now carves the landscape.
It doesn't just flow within it. Okay. One key systems thinking principle that helps grasp Python's far-reaching impact is isomorphism. This powerful idea suggests common patterns can be applied across different domains. Meaning, if an organizational structure, a design principle, a set of rules proves elegant and effective in one context, it often has the potential to work equally well, maybe even better, in a completely different domain. Python's core design, its elegant informational pattern, proved incredibly isomorphic.
Exactly. Python's elegant simplicity, its remarkable readability, its flexible, extensible nature proved to be an incredibly isomorphic pattern that flowed effortlessly and effectively into diverse, often initially unrelated fields. We see this vividly. In web development, frameworks like Django and Flask capitalized on Python's power, letting developers rapidly create complex, scalable web apps with significantly less boilerplate than many competitors. Python's clear syntax and rich ecosystem made it ideal for both front-end and back-end, dramatically lowering the barrier for a new generation, prioritizing speed and maintainability. Then, scientific computing. Libraries like NumPy for numerical stuff and SciPy for scientific and technical computing, they fundamentally transformed Python into the lingua franca of research and data analysis. Before Python, scientists often relied on expensive software like MATLAB or niche languages like R or Fortran. Python offered an open-source, flexible alternative that could seamlessly integrate with existing C-Fortran libraries, provide powerful data structures, facilitate complex calculations, stats, data visualization with surprising ease. It bridged the gap between theory and computation. And most recently, it has become the undisputed river of choice, for the explosion in AI and machine learning. Frameworks like TensorFlow, PyTorch, cutting-edge AI research and deployment primarily built on Python. Its existing scientific libraries, ease of prototyping, vibrant community support, its capacity as a glue language for high-performance C++ or CDA backends made it the ideal platform for developing, experimenting with, deploying complex neural nets and ML models. Its flexibility let researchers iterate rapidly, critical in such a fast-moving field.
So in each of these wildly different domains, Python's core informational pattern, its inherent readability, simplicity, and extensibility, proved universally effective. Not just good for one thing, good for many things, because its fundamental design principles were so robust and adaptable. This is a profound testament to the power of its design. Shows that a well-conceived, adaptable system can find utility and foster innovation in places its creators never even envisioned. Ultimate proof of its versatility and capacity to transcend its initial purpose.
And with this massive expansion into diverse domains, something else equally vital emerged: a distinct culture. And significantly, a profound sense of self-awareness within the Python community. It wasn't just technical rules, it was becoming a way of thinking, a shared philosophy guiding its collective evolution.
And its purest codification, the absolute essence of this culture, can be found in Tim Peters' now famous Zen of Python. What's truly remarkable, demonstrating this self-awareness, is you can access these guiding principles just by typing import this into any Python interpreter. It's right there, baked in, a constant reminder of its core values.
This collection of aphorisms, phrases like beautiful is better than ugly, simple is better than complex, readability counts, explicit is better than implicit, error should never pass silently, it's far more than a style guide. It is truly the system's declaration of its values, its philosophical DNA. It outlines the shared ideals, defining what it means to be Pythonic, guiding not just what code should do, but how it should be written for long-term maintainability and collaboration. Explicit is better than implicit, for instance, directly counters the magic in other languages, encouraging clear code paths.
And the impact of this Zen is profound. It provides a shared mental model that guides the choices of hundreds of thousands of developers, fostering remarkable coherence and consistency across a globally distributed system of millions. Imagine a collective consciousness subtly shaping decisions from a small script by a hobbyist to a massive application by a tech giant. This shared philosophy helps maintain the language's character as it grows, ensuring Python code often retains a recognizable, elegant style. It's an emergent form of collective intelligence, ensuring the river maintains its character even as it widens.
Now, if we're looking for the clearest, most dramatic illustration of Python's maturation into a level 3 social system, no event stands out more than its evolution and governance. This truly showcases its capacity for collective choice and self-determination, moving beyond reliance on just one individual.
For many years, as most familiar with Python's history know, Guido van Rossum, its creator, reigned as the benevolent dictator for life, or BDFL. This model, one person having final say, was incredibly effective for guiding early growth, provided clear, consistent, authoritative direction when the community was smaller, challenges less diverse, need for rapid consensus paramount. Guido's vision was instrumental.
However, this model eventually came under immense strain as the community swelled to millions of developers, users, stakeholders. A single individual, no matter how benevolent or insightful, just couldn't effectively manage the increasing diversity of opinions, the sheer volume of proposals, the accelerating pace. The contentious debate over the walrus operator, PPU 592, in 2018 became the undeniable breaking point. The walrus operator introduced new syntax for assignment expressions, seemingly small, but it sparked an incredibly intense, widespread debate, touching fundamental philosophical questions in Python's Zen readability, explicitness, the very aesthetic of Pythonic code. Opponents argued it made code less readable, could lead to clever but obscure constructs. Proponents emphasized its utility, reducing verbosity, improving efficiency sometimes. The intensity of this technical discussion basically revealed the immense potential energy of conflicting philosophies within the community, ultimately generating enough systemic pressure to force a reshaping of Python's governance material in Level 3.
The pressure from this debate became so immense, so consuming, that Guido made the incredibly significant decision to step down as BDFL. His words then were very telling, reflecting a deep understanding of the system's needs. "I don't want to have to fight so hard for a PP that I'm withdrawing myself permanently from the decision process." It wasn't just resignation. It was acknowledging the system had naturally outgrown its original centralized governance. The river had become too vast for one captain.
This leadership vacuum, this moment of profound uncertainty, forced the system to evolve. A crisis spurred innovation in governance. The community's response was to formalize the principle of choice most democratically. They deliberated, debated, then ultimately chose a new model of governance, a democratically elected 5-person steering council. This body, elected by core developers, would now collectively make major decisions, ensuring broader representation, shared responsibility.
And this, you see, was a profound transition from a monarchy to a republic in the truest sense. Not just a change of leader, a fundamental shift from a single point of control to a distributed, collective decision-making process. For anyone studying complex social systems, this was ultimate proof that the Python ecosystem was a mature, resilient social organization capable of determining its own destiny. It had truly become self-governing, demonstrating a level of emergent collective decision-making that's rare and powerful.
Of course, no complex system, especially a dynamic social one, develops without facing huge challenges, periods of profound stress. Python's resilience was severely tested by what many remember as the painful decade-long transition from Python 2 to Python 3, a period of immense systemic stress that threatened to fracture the community.
Yeah, this wasn't minor. It was a fundamental, backward incompatible change. Technically necessary for the language's long-term health addressing design flaws, preparing for a more global Unicode future, but it unfortunately created a deep schism in the community. Imagine a river suddenly facing a massive bifurcation, a systemic stress threatening to split the river in two, with countless code bases, libraries, developers entrenched on opposing sides. Technical differences like Python 2's print statement versus Python 3's print function, or integer division handling, and most significantly, the fundamental shift in how Python 3 treated strings as Unicode by default. It created immense migration headaches, a genuine threat to Python's unity.
Yet the system adapted. Despite the initial pain, cost, division, the system adapted in remarkable, ultimately successful ways. This included developing sophisticated migration tools like 2 to 3 to automatically convert code, and libraries like 6 allowing code compatible with both versions. There was clear, consistent communication from the PSF about the necessity, the path forward, the eventual end of life for Python 2, and crucially, the leadership of major companies migrating their code bases, setting a powerful example, providing critical momentum. Companies like Google, Dropbox invested heavily, signaling confidence, pushing the ecosystem. Slowly, painstakingly, through collective effort, sheer perseverance, the community rallied and healed the rift.
What stands out here is that this difficult period, much like a fever, ultimately strengthened the system. It forced introspection, demanded collaboration, a collective, painful effort. In the end, it left Python more robust and unified, with a modern, future-proof foundation, showcasing its incredible capacity for self-healing, long-term adaptation against existential challenges, a crucible that forged an even stronger community and language. So we've traced Python's incredible arc, from a frustrated programmer's quiet insight through the genesis of its code, the organic birth of its community, its eventual role as a global cultural force. It's been quite a journey, hasn't it? An emergent serpent truly becoming a mighty river. And now, as our deep dive draws to a close, it's time to distill the core, profound lessons from this amazing story. #outro. We've traveled with Python from its humble beginnings as a simple script, elegant informational rules crafted in solitary insight, to its current status as a global standard, permeating almost every aspect of tech and science. We saw its birth as pure information in Level 1, its emergence as a living, self-regulating community in Level 2, and its ultimate ascent to a culture-shaping, self-governing force in Level 3.
And the core lesson here is profound. Python's unparalleled success isn't just brilliant technical design, though it has that. It is, more significantly, the emergent consequence of a system that was fundamentally open, incredibly adaptive, and deeply interconnected with its human community. It wasn't just built and deployed. It grew incrementally, dynamically, often unpredictably, in constant conversation with the needs and contributions of the world around it.
And Python's story truly is a perfect, vibrant illustration of our river of reality framework. It began with foundational information, its code, clean syntax, elegant rules, Level 1 emergence, a perfectly crafted artifact. Then, when open to the energy of human creativity and frustration, and the raw material of a global community eager to contribute, it gave rise to a living, self-regulating ecosystem in Level 2, capable of metabolism, adaptation, self-organization. And finally, this ecosystem matured into a complex social organization with its own distinct culture, its values in the Zen of Python, and a formalized capacity for collective choice, allowing it to shape the technological landscape globally, embodying Level 3 emergence in its fullest form.
Python is truly more than just a tool. It's a powerful testament to the transformative power of emergence. It teaches us that the most resilient, impactful, enduring systems are rarely those perfectly engineered and closed off from the start, thinking they have all the answers. Rather, the systems that thrive are those allowed to grow, learn, adapt, evolve in constant dynamic conversation with their environment, embracing feedback, navigating challenges, collectively determining their own destiny. It's a profound lesson in how complex, distributed intelligence can emerge from simple rules and open interaction.
That's such a powerful and inspiring thought. This mighty river of Python continues to flow, shaping our world in ways its creator probably never could have imagined. And our challenge to you, the listener, as you finish this deep dive, is to now look around your own fields, your own lives, with this framework in mind. What other serpents do you see, maybe humble now, that are on their own journey, slowly but surely becoming mighty rivers, shaping the world in unexpected, emergent ways? Think about it in open source projects, scientific theories, social movements, evolving tech. You might just begin to see the hidden forces of emergent change all around you, constantly at work. Thank you for joining us on the Deep Dive.